All right, this is the condensed version of chapter 20 because I've got a short amount of time, but we're going to get through it. Okay, so we're going to talk about hypothesis testing today. In order to talk about that, I'm using the example from the book, but you need some context, so I need to read you something from the book real fast. Ingots, huge pieces of metal, often weighing more than 1,000 pounds, made in a giant mold. They must be cast in one large piece for use in fabricating large structural parts for cars and planes. If they crack while being made, the crack can propagate into the zone required for the part, compromising its integrity. Airplane manufacturers insist that metal for their planes be defect-free, so the ingot must be made over if any cracking is detected. So if there's any cracking, they melt it all back down and start over again. Now, they think that crack about 20% of the time. Okay? 20% of the time. Obviously, that doesn't sound very good. They're cracking 20% of the time. They're melting down a lot of things and restarting a lot of the time. So they're trying to find some process that would reduce this cracking percentage. Okay? So they did a sample, and I'll talk about that in a second. But then how do you know if your sample result is just because of sampling variability or evidence that this new process? That's the type of question we can answer with a hypothesis test. All right? So they have a sample of 400 ingots with this new method. And they came up with 15% cracked instead of the 20% that's believed. Okay? So you have a p 17% sample. And then you have 20% is what's happening, they think, in the population for like all ingots. Everyone with me? Okay. Again, we're trying to see if that 17% is significant or not. That's what we're always going to be looking for in the hypothesis test. Is that enough evidence? Okay? Or is it just sample to sample variability? All right. Test. There are 4 sections, and you will always have to have all 4 sections. At no point in the AP exam are they going to say, complete a hypothesis test, and then list out the sections for you. They're going to say, here's a scenario, and they're not going to say to do a hypothesis test. They're going to say, provide statistical evidence that. And that means you're supposed to do a hypothesis test. Okay? So you have to infer from the question what you're supposed to do, and then know all the steps and processes to that. So even if you don't take notes, and you're not a note-taking person, you better take notes today, because you got 4 steps you got to know. All right? The first one is writing hypotheses. We're doing a hypothesis test. You better have some sort of hypothesis. Every hypothesis test has 2 hypotheses. The first is the null hypothesis. The null hypothesis says that nothing has changed. It's the same as what it is in the population, and nothing has changed. Everything is great. The second hypothesis is the alternative hypothesis. And that says, oh, maybe something's changed. So you have the null hypothesis, you have the alternative hypothesis. There's symbols for both of those. H sub 0, which we say H naught, that's the null hypothesis. H sub A, that's the alternative hypothesis. Now, your null hypothesis, no matter what the test you're doing, is always the parameter you're looking at equals whatever you think that parameter is. You have 2 things in this class that I keep saying, but you guys don't actually have the vocabulary down yet, so I'm going to keep reminding you. In this chapter, we're just talking about proportions, but we have 2 different proportions to keep track of. You have a statistic, and you have a parameter. The statistic is what's happening in your sample, and that's p hat. The parameter is what's happening in the population, so that's p. All right? So your hypotheses will always be in terms of the parameter, so they will always be in terms of what's happening in the population, not what's happening in your sample. All right? Then your alternative will show what you think is happening. You think it's increasing, decreasing, or that there's just no change. So, using this INGOTS example, right? We think that in general, they're cracking 20% of the time, and we're hoping to reduce that amount. So if I'm going to write the hypotheses for this, our null hypothesis will be that P is equal to 0.2. We're saying there is no change, but we think it's happening in the population. We think the population proportion is 0.2. I'm not using P hat, I'm using P and what I think P is. Don't use P hat, you'll be wrong. My alternative, I want this cracking proportion to decrease. So hopefully, we want P to be less than 0.2. That is the format your hypotheses are going to be in for this chapter. In other chapters, they're going to be in the same format. They're just going to have different parameter values because we won't be talking about proportions all the time. Okay? So, P equals 0.2. Then your alternative, your null is always going to be P equals something. And your alternative will be that P is changing. So how is it changing? You can have a one-sided alternative hypothesis or a two-sided alternative hypothesis. For our INGOTS example, we have a one-sided alternative. We think, or we want, the cracking percentage to decrease. So we want it to be less than 0.2. In some scenario, maybe I want something to increase. So I'd want that proportion to be greater than whatever is happening in the population. That's a one-sided alternative when you have greater than or less than. There are scenarios where you might have a two-sided alternative. You don't care if it's increasing or decreasing. You are concerned if there has been a change at all. So if there's a change, we would say P is not equal to as our alternative. All right? So we're just thinking it might have increased, might have decreased, it's just changed somehow. Okay? Yeah? So everyone good with how I wrote these hypotheses? Because that's what we're going to do right now. We're going to practice writing hypotheses. That's the first step of writing hypotheses. All right, so here's two. We're going to do two of these three examples. We're writing the null and alternative for both. Let's do A. A governor is concerned about his negatives, the percentage of state residents who express disapproval of his job performance. His political committee pays for a series of TV ads, hoping that they can keep the negatives below 30%. They will use follow-up polling to assess the ads' effectiveness. So I have to have a null hypothesis, and I have to have an alternative hypothesis. The null is P equals something, and the alternative is P is changing somehow. What is the null hypothesis? P equals 0.3. They said they want to keep the negatives below 30%. So if nothing had changed, we would think that it stayed around 30%. The alternative, they want it to be below 30%. So what should the alternative say? P is less than 0.3. Notice those numbers are always the same. Do not use what's happening in the sample. It would be very tempting, like in the INGOTS example we're doing, you have this 0.17 you could use. Do not use that in your hypotheses. Do not use your sample proportions in your hypotheses. All right, on B, is a coin fair? Doesn't give you very much information, but you should be able to figure this out. What's your null hypothesis if a coin is fair? P equals 0.5. For your alternative, what are you going to write? P doesn't equal 0.5. I don't know if maybe it's going to be different on one or the other. I just want to know if it's changed, right? If it's not fair, it has changed in some way. Okay? So A is a one-sided alternative. B is an example of a two-sided alternative. Are we good with hypotheses? Excellent. That's the first step. That's a really short step. Woo! No. Step 2 is the model. Let me read this to you since you don't like to listen to me when I say things. To plan a statistical hypothesis test, you have to specify the model you'll use to test the null hypothesis and the parameter of interest. And then I highlighted. Of course, all models require assumptions. So you will need to state them and check any corresponding conditions. So step 2, you check your assumptions and conditions. Let's go over those really quickly since they're not written down here because we've done them already for 2 chapters in a row. You have the independence assumption. If you want to write that you assume that the 2, whatever you're doing, are independent, or whatever you're checking is independent, please do. After the independence assumption, you check that using the randomization condition. If it says it's a random sample, then you can say it's a random sample. If it doesn't say it's a random sample, then you need to say that you think that however many, whatever you checked, is a good representation of the population of whatever you're checking. Okay? After that, less than 10%. Is your sample size less than 10% of the population? Make sure that's in context. Do not write 400 is less than 10%, period. That doesn't count. Do not write 400 is less than 10% of the population. That doesn't count. In context. So 400 is less than 10% of all ingots that could be cast. You give what the population is. Lastly, is your sample size assumption. Since we're just dealing with proportions in this chapter, you'll be doing success failure. Is n times p greater than or equal to 10? Is n times q greater than or equal to 10? I need to show that. Okay? So, you write your hypotheses, you check your conditions. Now, we talked about this in chapter 19. I'm going to talk about it again here. You now know how to do 2 things. Well, you're going to in a second. You know how to do a confidence interval. And after all this, you're going to know how to do a hypothesis test. So you need to write a sentence explaining what you are planning on doing. I checked the conditions for why. All right? So because the conditions are met, because the conditions are satisfied, because the conditions are whatever, I can perform or I can construct, depending on what you're doing. In chapter 19, you could construct a 1 proportion z interval. Now we're not doing intervals. We're doing a test. So guess what the test is called? The 1 proportion z test. I mean, they're naming things these really complicated things. But you need to identify what you're doing. That's a very crucial piece of what's happening. Okay? Yeah? So you check the conditions, you write a sentence. That's step 2. Everyone good with that? Hypotheses, condition, sentence. So far, we're good. All right. Step 3 then is the mechanics. Mechanics meaning the actual calculations, the work you're going to show to do the test. Now, the ultimate goal, you want to get a probability. I want to know what's the probability in this scenario. What's the probability that I would conduct a sample and get a 17% cracking rate? That's what I'm calculating. All right. What's the probability that I do that? So here is the math. You're going to find a z-score, just like you found a z-score in chapter 6. All right? So in order to find the z-score, you take the sample proportion minus your population proportion. So in this case, I have 0.17 minus 0.2. In my sample, 17% of the ingots cracked. I think from previous information that 20% of them crack on a normal basis. Right? So sample minus the null divided by the standard deviation. You are not using p hat and q hat in the standard deviation because we know p. In chapter 18, we used p, right? In chapter 19, we used p hat because we didn't know p. So we estimated. So we had the standard error. But now we know p again, so we're going back to using p. If you have the population proportion, you should use it. You shouldn't estimate. Okay, so I have divided by the standard deviation. I've got 0.2 times 0.8 divided by the sample size happened to be 400. All right. That's going to give you a z-score. Remember, a z-score is how far away in standard deviations you are from the mean in a standard normal curve where the mean is 0 and the standard deviation is 1. Okay, that's what you're getting. All of this formula stuff. The standard deviation equation, is that on the formula sheet? Yes, it is. Is the z-score? Well, sort of. Just like the confidence interval, with different tests, we use different models. Sometimes we use z, sometimes we use t, different things going on. So they give it to you in words. So you're expected to be able to put it into words. Okay? So it says on the formula sheet, standardized test statistic. In this case, that is z. I'm looking for a z-score. It says stat minus parameter. Again, the statistic is something you sampled. The parameters from your population. All right? So you have to know that vocabulary. So if you know statistic is a sample for parameters population, then you know it's p hat minus p. And then divided by the standard deviation of the statistic, which again, that formula is on the formula sheet. Okay? So you're going to show the work to find a z-score, and then you're going to find a probability, which is on the next page. So the mechanics is two things. Finding a z-score, finding a probability. So here is that work I just did. Their z-score is negative 1.5. Now keep in mind that our alternative said we think that the parameter is now less than 0.2, right? Keep that in mind, back of your mind. Okay? Now if we have a z-score, that means we have a standard normal curve, the mean of 0, standard deviation of 1. So negative 1.5 is right there. They draw the line for you. Why then did I want to find the area to the left? Why did they shade that part? Because it's less than. In our alternative, we said we wanted the population proportion to decrease. So I know the probability that it's that z-score or less. Okay? If it said greater than, we would have gone the opposite direction. If it said not equal to, we do something a little bit different, and I'll talk about that next week. Okay? So, normal CDF from negative infinity to negative 1.5, right? Gives us this number. That's the probability. That's our p-value. Okay? So 6.7% of the time, I could get a sample result of 17% cracking. Okay? So management must now decide whether an event that would happen 6.7% of the time by chance is strong enough evidence to conclude that the true cracking proportion has decreased. If something happens 6.7% of the time, is that super unusual? Not super unusual, and we want it to be super unusual. All right, so 6.7% of the time is not super unusual. If it was like 0.2% of the time, that would be unusual, right? So we've got 3 steps, keeping track. Hypotheses, conditions, did the work, found this p-value. That's the whole point. We're trying to find this probability. That's called a p-value. You're trying to find this probability. Then you're going to have to make a conclusion based on this probability. For now, your threshold for what is unusual and what is not unusual is 5%. Anything less than 5% is going to be unusual for now, until I say otherwise. All right, anything over 5% is not unusual. Okay? So since I could get this sample with the 17% cracking rate 6.7% of the time, that's not super unusual. So I can't conclude that things have changed. Does that make sense? Yeah. If it was below that, if it was 0.2%, then that is super unusual, and that wouldn't happen very often. So I can conclude then that maybe things have changed. Okay? So the last step is making a conclusion statement, and there is a specific way we write those. When the p-value is high, so your probability is high. Again, like I said, our threshold right now is 0.05. So when your p-value is above 0.05, we haven't seen anything unlikely or surprising. So there's no reason there's been any change. So pretty much we're agreeing with what the null hypothesis says, right? So we say we fail to reject the null hypothesis. We do not accept the null hypothesis. We fail to reject it. We have not found conclusive evidence to reject it. But we also had a sample that was less than 20%, so that is not out of the realm of possibility either. Okay? So we do not accept that p equals 0.2. We just fail to reject that p equals 0.2. So make sure you know that. Fail to reject. That's a very important thing. It's going to keep coming up. If the p-value is low, like I said, our threshold is 0.05, so it's less than 5%. Then we reject the null hypothesis. We have information that's unlikely given our null hypothesis, given that in the population it's 0.2 or 20% cracking rate, then we would have seen what happened in our sample rarely. So that is conclusive evidence that maybe it has decreased. So we reject the null hypothesis. So in summary, there you go. If it's high, we fail to reject because there's not enough evidence of a change. If it's low, we reject because there's evidence of a change. Yeah? So hypotheses, conditions, statement about what you're going to do, mechanics, conclusion. Your conclusion should be in context if possible. There's no reason it shouldn't be, so try to put it in context. Next week or tomorrow, whenever we're here, because of snow, whatever, we'll go into more detail about those p-values and about how to explain your conclusion. But in general, right now, does everyone have the steps, sort of? Okay. Then this is what I would like for you to do for homework. I want you to read chapter 20. I just pretty much summarized all of it, but read over chapter 20, paying attention to the examples, because they worked them all the way through with all those steps. Okay? So read chapter 20. There's especially a good part in there about comparing why we say fail to reject instead of we accept and that kind of thing, comparing it to trial by jury. It's a good comparison. Read through that. Okay? But read chapter 20 again. Then on page 476, you're going to do number 2. That's just a question about hypotheses. You can write hypotheses. I've got full faith that you can do that part. And then I want you to try a hypothesis test. So try number 14. I am fully aware I have not done an example. So I have not worked one of these through with you all the way. I've done the one from the book. We kind of talked about that one. But you have all the steps, so try to do 14. 14 splits it up for you A, B, C, D into all the steps. So say write some hypotheses. Check your conditions. Do this, okay? So try that out.